After fluorescent lights and all, some of you may be wondering what the difference is between fluorescence and phosphorescence, and that's going to be explained in the next few videos. We see here how immediately after the energy is applied, fluorescence takes place, and immediately after it's taken away, it ends. Which is very different compared to phosphorescence, which continues to take place after the energy is removed. And now to explain it is me from the past. Hey guys, so I decided through lack of easily understandable phosphorescence diagrams and the necessity for this to be taught to you, I decided I might as well teach you through a video with my whiteboard. So, everyone remembers how in Chem 1, electrons can absorb radiation and jump up in energy level as they become excited. So, this is the part of it that we already know. This is the ground state going into an excited singlet state by absorbing a photon. So if you look here, because of the Paoli exclusion principle, the spins are opposite on these two electrons, and up here, even as one goes up and the other stays, they're still opposite. This is because it has a charge of plus or minus 1/2, and when they're like this, when they're both opposite, it's called anti-parallel. So the charges cancel out, means nothing, and it makes it very easy for the electron to release a photon as light, jump back down in energy level. That's it. But sometimes, same way, sometimes you find out that, through a small percent chance, one kid, you find out you're having triplets. It's the same thing. Over here, it goes from an excited single state to an excited triplet state through intersystem crossing. Intersystem crossing works off like if there's a large enough molecule and it's paramagnetic and things like that, then sometimes when it jumps up in energy level, the spin will get screwed up, so now they're both spinning the same way. They have parallel spin over here. Right here. See, they're both going the same way. Problem with that is now they have a non-zero value for the charge overall, and that's not good. So in order to go down, it's difficult to exit the excited triplet state. So the next step is to go through something called vibrational relaxation, where it releases some of its pent-up energy throughout the molecule or to the surrounding molecules so that it can get to a slightly lower energy level. And then from there, it gets to release the light as phosphorescence to go back down to the ground state. The thing is that this takes much longer than it does for something like fluorescence, where it's just happens immediately like that, This extra time and the fact that only by a small chance does intersystem crossing occur and it gets stuck in a triplet state, it means that it takes so much longer than usual to undergo the process to release light that it kind of traps light like a reservoir for a long period of time where it can release its glow for an extended period. Thanks, me. So now we have a great big bottle of drugs. Not what this actually is zinc sulfide, an extremely common compound used in the manufacturing of glow-in-the-dark materials. Out of the two compounds used, it is more common than the other due to its low manufacturing cost. The other compound used is strontium aluminate, which here in this low quality picture you can see a side-by-side comparison between the two of them. Zinc sulfide on the left, strontium aluminate on the right. Strontium aluminate has a higher cost due to its greater ability to phosphoresce and the expensiveness of the materials required to manufacture it.